Let's now turn to the MapReduce paradigm itself. As we just mentioned, it's a data parallel paradigm with message passing. It's also a pipelined procedure where there are two phases. There's the map phase and the reduce phase. Further, as we also mentioned, it's a higher level abstraction, so programmers only need to specify what each mapper actually does and what each reducer actually does, and the MapReduce implementation takes care of all the message passing required between the two phases. In fact, one doesn't even need to worry about how many processors there are and which ones should be doing what kind of job, map or reduce. That's all left to the MapReduce implementation. All a programmer needs to do is define their task in terms of the MapReduce paradigm, which we'll come to in a moment, point the system at the data on which they would like this task performed, and the MapReduce implementation figures out which processors can be made available to this task and does the rest without the programmer having to worry about the details. That's what makes MapReduce exceedingly powerful for large-scale data parallel processing, since it bridges the gap between high-level specification of an algorithm and its massively parallel implementation in a manner which has really never been successfully done ever before in the history of parallel computing. As we shall see, many complex web intelligence algorithms for machine learning and processing big data are easy to express using the MapReduce paradigm, making their large-scale parallel implementation much easier than if one had to program these using either shared memory or low-level message passing, as was the case before MapReduce. The most common example used to explain MapReduce is that of counting words in documents, something we've seen last week when we tried to compute inverse document frequencies, for example. Suppose we're given many documents. In this case, say there are only 10 documents here, but there could be, hundreds of thousands or even millions of documents, and we need to compute the frequency that each word takes across this whole set of documents. And we'd like to do it in parallel using many processors so as to reduce the overall execution time. In our simple example, we'll take only 10 documents and 3 mapper processors which execute map tasks, followed by 2 reducer processors that execute reduce tasks. Of course, once the mapper processors are done, they can start doing their reduce work, so the total number of processors need not be 5, it might even be as low as 3 or maybe 4. The mappers are given data. In this case, there are documents identified by document IDs, which the MapReduce system randomly distributes across the different mapper processors. Each mapper processor thus gets a bunch of documents. It doesn't really know which documents it's getting, it just gets a bunch of them in any random order. Now here's how the problem is defined in terms of map and reduce tasks. Remember, a mapper simply needs to perform a whole bunch of map tasks on all the documents that it gets. So it's getting a sequence of document IDs followed by the contents of the document. In other words, it's getting a key and a value and a sequence of such key-value pairs. A map task works on a key-value pair, such as a document ID and its contents, and produces a bunch of key-value pairs, in this case, words and the frequencies with which they occur in this particular document. Remember that a map task acts on one key-value pair, so it needs to act in this case on one document, It is, however, free to emit many key value pairs as its output. In this case, the many words that occur in that document along with their frequencies. For example, the map tasks for the document D1 would be to emit a W1 followed by a 1, a W2 followed by a 1, and a W4 followed by a 1, and similarly for the other documents. In some cases, such as D6, we would emit a W2 followed by a 2, but in most other cases it would be a count of 1. The second part of our problem definition is the reduce phase, in which a list of key value pairs corresponding to the same W key, in this case, is reduced or compressed or combined into one key value pair for that particular key. So for example, all the counts for a particular word are summed up in the reduce phase to create one key value pair for each word. Now clearly, in order to perform the reduce function, all the key value pairs for a particular word need to be together if they are to be so summed up. Unfortunately, since each mapper acted on an independent set of documents, it only has access to those word count pairs for the particular documents it happened to see. The best that a mapper could do is compute the reduce function using the pairs that it happens to have available. So for example, this mapper, it only had these two documents, D1 and D2, which had a W1, so it computes a W1 comma 2 by performing the map and reduce functions on the set of documents that it has available to it. Similarly, this mapper adds up the sums for W2 across all its documents to get a value of W2 comma 4. Of course, that is not enough. All these partial summations themselves need to be summed up, and this is where the MapReduce implementation comes in, and sends all the key value pairs with the same key to the same reducer so that they are all together and they can finally be reduced to get the right answer. So all the pairs having W1 manage to get to this reducer where they can get added up to get the correct value for W1. So we got W1 from here, we got a W1 from here, we got a W1 from here, and we added all of these up to get a value of 7. Similarly, the second reducer also manages to get all the key value pairs for each word to be together so that they could be added up. In this case, the first reducer works on pairs where the keys are W1 and W2, and the second reducer works on those where it's W3 and W4. So now we're ready to define MapReduce formally. Mappers read data in the form of key value pairs K1, V1, and for each such K1, V1 pair, a mapper may emit one or more pairs of the form K2, V2. In our word counting example, K1 was document ID, V1 was the contents of the document, whereas K2 was the word and V2 the number of times a word occurred in a particular document. The reduce function, on the other hand, receives all the pairs for some value of K2 and combines them through a reduce function. So the reduce of K2 and all the values that came out of the map phase for that particular value of k2 are combined using a function f sub r. In our word counting example, f sub r is just a summation across all the occurrences of a particular word in all the documents that we process. Some of you might have noticed that in our example we actually did some reduce work within the mappers, but we'll come to that point in a short while. For the moment, the strict definition of a map function is only a map, that is, from one key value pair produce one or more key value pairs, and a reduce function is take all the key value pairs for a particular value of the key and apply the reduce function on them. The MapReduce platform is responsible for routing pairs to reducers so that all the pairs for the same key end up at the same reducer. MapReduce essentially sorts the key value pairs that come out of the map phase so that they land up in the right place. The final very important point to note is that the MapReduce process reads data, possibly from a file system or a database, and writes fresh data. So it's a batch process that always produces more data. Very different from a database where one is querying data and just getting an answer.